Okay, so first we define capacitor. A capacitor, this is a device. Basically, it is formed by two plates that conducts and are separated by an insulator called dielectric. So it's just a two plate. So maybe a rectangular plate or any shape of plates that are in parallel with each other and are separated. So these two plates separated, the space between them is a dielectric. That is called a dielectric. Then this device or this instrument or this component, capacitor, can contain charge. It can be charged and it can be discharged simply by applying potential difference at both of the terminals of this capacitor. And so let's say the distance or the thickness of the dielectric T, then these are the conducting plates. So two conducting plates, then there is an area of that conducting plates. We can call it just A. A is the cross-sectional of the conducting plates. And so this is the capacitor. And the capacitance, this is the property of a capacitor and how well it can store electrical charges. So a property, just like resistance for a resistor, a capacitor, we can measure the quantity or how much energy can the capacitor store, and that's capacitance. The property of a capacitor on how well it can store electrical charges. This is somewhat similar with the battery. The only difference with the battery is the battery uses the chemical principles to store energy, while for the capacitance, it uses the principle of electrostatics. It stores charges or energy in an electric field. So that's the meaning of a capacitance or a capacitor. It uses the principle of electrostatic from electromagnetics. Then, the capacitance is measured with a unit. The unit is farad, named after Michael Faraday, F. Normal capacitors is usually the ratings of the capacitance ranges from nanofarad times 10 to the negative 9, microfarad times 10 to the negative 6, or can be picofarad times 10 to the negative 12. But there are other capacitors that can have large capacitance, just like the supercapacitors. Supercapacitors, these are capacitors that has higher electric charge density compared to normal capacitors. And usually the capacitance ranges from around 100 farad up to 500 farad. There's some capacitors can also the Maxwell capacitor. I think it's 3,000 farad of capacitance. Now, there are some available capacitors in the market. These examples of capacitors that you can see, different types of capacitors. The capacitors can be classified or with respect to their dielectrics. Some are called electrolytic capacitors, some are called ceramic capacitor because they use a ceramic as the dielectric. So these are examples of capacitors used in electronics circuits. So if you see devices that similar to these pictures, then they are capacitors. Now, how do we measure the capacitance of a capacitor based from the definition of a capacitance? A capacitance in mathematical form is the charge that can be stored for every unit of voltage across the terminals of the capacitor. So the 1 farad is actually equivalent to, if this is Q, this is coulomb, and the voltage is in volts. So 1 coulomb per volt. 1 farad is equivalent to 1 coulomb or coulomb per volt. Then, from this, we can also derive the capacitance of the capacitor given the cross-sectional area of the conducting plates and the thickness of the dielectric and the type of dielectric that is used for that capacitor. By using a formula, this formula, capacitance, is equal to the absolute permittivity, epsilon naught, times the relative permittivity of the dielectric. Multiply it with the cross-sectional area, and you divide this one with the thickness T of the dielectric, and the unit here will be in farad, where the area is in square meter, the thickness is also in meters. Then the epsilon naught, where epsilon naught is a constant, and this is equal to 8.854 times 10 to the negative 12 farad per meter. And epsilon r is the relative permittivity, and this is based on what type of dielectric is being used. For air, the relative permittivity is 1 for free space. But it all depends on what type of dielectric is in between the plates or the conducting plates of the capacitor. And if you multiply that, K, that will be epsilon naught times epsilon r. This is called the dielectric constant. Dielectric constant. And it is equal to epsilon naught when you are in free space, or the dielectric that is used is just a free space. Okay, then we can also put different layers of dielectric inside the capacitor. So if this is the capacitor, then we can put different types of dielectrics in between. So this can be the first dielectric, let's call this one D, the thickness. For the first one, let's just call it D1. And this is the first dielectric. Then for the second one, let's call it D2. Thickness is D2. And this is another type of dielectric. So let's call the first one the epsilon R1. The second one epsilon R2. Then the last one, let's call this D3. Then we have another dielectric here, epsilon R3. Now, if you want to determine the total capacitance of this type of capacitor, the formula will change because we have different permittivities for the dielectrics. So the total capacitance now for this one is this will be the formula epsilon naught times the area. The cross-sectional area is the same all throughout. The only difference is the dielectric uses different dielectrics. This will be equal to the first one, so the first thickness divided by its permittivity, epsilon R1, then plus D2 all over epsilon R2, then plus D3 all over epsilon R3. So if you have more than 3, you just add them here at the denominator of the formula. Okay, so this is capacitors with different dielectrics. Capacitors with different dielectrics. Then also we can derive the voltage across the capacitor or the current across the capacitor, taking the formula for the capacitance C equals Q over the voltage across it. So if we want to determine the current, we know that current, remember current is just equal to the rate of charge with respect to time, I dq dt. So if we solve for Q here, so dq is equal to I dt, and q will be equal to the integral of I dt. And we substitute this one in the first formula. Then we solve for the current. C will be equal to Q, which is the integral of I dt divided by E. Then, if we take the derivative, we cross multiply. So C is a constant times E because the integral of I dt. Then we take the derivative. So we have C dE equals I dt. Then solving for the current now will be equal to, this will be equal to C times the voltage, derivative of the voltage with respect to time. So this will be the formula for the current. Now, one property of a capacitor when we are charging a capacitor. So the capacitor will be full charge at some time. So if it's full charge, the current will be equal to 0. So this will be equal to 0 when the voltage is not changing anymore, or not increasing or decreasing or discharging or charging. So the current will become 0. Why? Because the capacitor now will be full charge. So this means that at when t approaches infinity, the capacitor acts when t approaching infinity. The capacitor acts like an open circuit. Why? Because the current when t approaching infinity is 0. So when it's equal to 0, there's no current flowing, then it acts like an open circuit. Okay? So this is capacitor and capacitance. Then let's take an example. This one. An uncharged 50 microfarad capacitor is connected to a 40 milliamp constant current source. Determine the voltage across the capacitor after 10 millisecond. So to solve this, we recall our formula before, the formula that we derived for current, this one, I equals C times dE dt, or dV dt, if you like to use the V as your voltage. So I equals C times dV dt, where V here is the voltage across the capacitor. So we can derive the voltage here. So by cross multiplying, so this will be 1 over C I times dt equals dV. Then taking the integral of both sides, so V now will be equal to, the integral 1 over C, the integral of I dt. So this is another formula. This is the voltage across the capacitor. And we can use this one to determine the voltage across the capacitor after 10 millisecond. And to do that, so we need the current. What's the current? It's a constant current source. So if it's a constant current, then we can just move the current to outside the integral sign. But if it's not constant, if it's changing through the time, then you need to integrate that one. So this will be 1 over 50 microfarad. So 50 times 10 to the negative 6, it's micro. Then we move the current outside the integral sign. So this will be 40 milliamps times 10 to the negative 3. Then integral of dt. So we have a limit from 0 to until 10 millisecond, or this is equal to 0.01 second. And calculating this one, the voltage now will be just equal to 40 times 10 to the negative 3 all over 50 times 10 to the negative 6. We multiply this with 0.01. Then you multiply it with the ratio, this ratio, then the voltage will be equal to 8 volts. So the voltage across the capacitor, if it's being charged by a constant current source of 40 milliamps, will be equal to 8 volts if it's initially uncharged. Remember, if it's initially uncharged after 10 milliseconds. So that's how we compute for the voltage using that formula. Now, for the other example, here, we want to determine the capacitance. Calculate the capacitance between two parallel plates, each of which is 100 square centimeter and 2 millimeter apart in air. In air means the dielectric is air. So meaning epsilon r will be equal to 1. So we will be using 1 as epsilon r. So the formula that we will be using is the other one. The capacitance is equal to epsilon o naught multiplied by epsilon r times the cross-sectional area of the plate divided by its thickness, or the thickness of the dielectric, or the distance between the two plates. So epsilon naught is constant. It's just equal to 8.854 times 10 to the negative 12. 8.854 times 10 to the negative 12. You can use your calculator. It's in your constant. In your calculator. I don't know the number, constant 18 or 32. Epsilon r will be equal to 1. Why? Because this is in free space. Then we need to convert the area into square meter because the formula is in square meter. The given area is in square centimeter. So 100 square centimeter, we convert this one into meters. Then you multiply it with 100 centimeter for 1 meter. Then you square this one. So this will be equivalent to 0.01 square meter. And for the thickness, it's also in millimeter. So we need to convert that into meters. So 2 millimeter. 1 meter is equivalent to how many millimeter? is equivalent to 1,000 millimeters. And this will be equal to 0.002 meters. Then we can now substitute these values to the formula to solve for the capacitance. So epsilon 8.854 times 10 to the negative 12. So the unit is farad per meter. You multiply this with the area, which is 0.01 square meter. Then you divide this one with, we forgot to multiply it by 1, the relative permittivity of free space. Then all over the thickness, which is 0.002 meters. Then we can cancel out some units here, meter, 1 meter here, then another meter and meter. So the remaining unit is in farad, so it's correct. The unit for capacitance should be in farad. Then calculating this will be equal to 0. I'm not sure with this answer, 4427 times 10 to the negative 12 farad, or this is a picofarad if you want to use the prefix pico. So this will be the answer. The capacitance of that capacitor is equal to this one. So that's how we use the two formulas that we derive here. Then now, just like resistors in circuits, we connect resistors in different ways. We can connect them in series, parallel, or the combination parallel series. Then we solve for the equivalent resistance or the total resistance. In capacitors, we can also do that. So we can connect them first in series, capacitors in series. In series. What will happen to the capacitance the total capacitance if we connect them in series? So if we have here 3 capacitors, so this is the symbol for capacitors, just 2 plates. Just like the exact composition of the capacitor. So this will be the total capacitance. If this is C1, C2, and C3, what will be the total capacitance if they are in series? So to solve this, it's not the sum of the individual capacitance. Unlike the resistance, we just add them all. In capacitors, it's the other way around. We use the formula in parallel, in resistors or resistance, here in series for capacitors. So what is our formula in resistors? It's just 1 over R1 plus 1 over R2 plus 1 over R3. So here in capacitance in series, we also use that. So this will be 1 over C1 plus 1 over C2 and plus 1 over C3. It's the other way around. Then the charge, the total charge will be the sum of the charges at the different capacitors, Q1, Q2 plus Q3. While the voltage is also the sum, E1, the voltage across capacitor 1 plus the voltage across capacitor 2 plus the voltage across capacitor 3. So the only formula that change is the total capacitance. Now if we connect them in parallel, capacitors in parallel, what will happen to the capacitance when they are connected in parallel? So if we connect them in series, the total capacitance decreases, isn't it? Here. So if you have 50 farad, 50 farad, 50 farad, if you connect them in series, then the total capacitance will be 50 over 3. It's smaller. So you decrease the capacitance by connecting them in series. While in parallel, it's the other way around. Why? Because for parallel capacitance, we use the series formula in resistors. So this is C1, C2, and C3. And this will be the equivalent C. C total now will be equal to the sum of all the capacitors that are connected in series. C1 plus C2 plus C3. So that's how we solve for the total capacitance of capacitors in series and series parallel. We can also use the different theorems or principles in resistors here. Then, because we are storing charges inside the capacitor, we basically stores energy because it's just like a battery. You need to store. It's a way of storing electrical energy through an electric field. So now, how much energy are we storing inside a capacitor? How do we solve for the energy? So energy stored in a capacitor. Unlike the resistor does not store energy. It dissipates or consumes energy. It transforms that energy into another form. Maybe it transforms it to heat energy. But for capacitor, it does not consume energy. Ideal capacitors does not consume energy. It only stores energy. So the energy that is being stored, let's call it W, for a capacitor is just equal to 1/2 the capacitance multiplied by the voltage of that capacitor. So another way to solve this in terms of, if you don't know the capacitance, in terms of the charge, is 1/2 Q times E. Why times E? Because capacitance is equal to Q all over E. So if you substitute Q all over E, the E at the top, this E squared will cancel out with the E at the bottom or the denominator. So it will be equal to Q times the voltage. And in terms of the capacitance and charge, this will be equal to 1/2 Q squared all over the capacitance. And the unit for W here, this is the energy, is in joules. While C is in coulomb. So this is J, this is C, and E is the voltage across the capacitor in volts. And capacitance, this should be Q here. C, the capacitance, this should be in farad. Farad, F. Okay? Let's take an example. A 50 microfarad capacitor is charged to 300 microcoulomb. An uncharged 100 microfarad capacitor is then connected in parallel with the first capacitor. Now, evaluate the charge transferred to the 100 microfarad capacitor. So, how much charge is being transferred from the charged capacitor, which is the 50 microfarad, to the uncharged, which is the 100 microfarad capacitor. So, let's say C1 will be equal to 50 microfarad. That's the first capacitor. And Q1 will be the charge, initial charge of the first capacitor, 300 microcoulomb. And C2 will be the capacitance of the second capacitor. Then we want to determine the charge that is transferred to the 100 microfarad or the second capacitor. So let's recall, what is the formula? What's the relationship between this Q, C, and also the voltage across a capacitor? So we know that the voltage is actually, or the capacitance, let's say the capacitance from our formula is Q all over the voltage. So if you solve for the charge is just equal to the product of the capacitance and the voltage. Now, the voltage across the two capacitors, because they are connected in parallel, They're connected across each other. So it means that the voltage across them both are equal. So V1 is just the same as V2 because they're connected in parallel, and let's just call it V. So for the first charge, Q1 will be equal to the capacitance 1, the first capacitance times the voltage. Then for Q2, then this will be the second capacitance times also the same voltage. Then C1 is 50 microfarad and C2 is 100 microfarad. Then we can divide these two to determine our Q2. So dividing Q1 and Q2, so Q1 all over Q2 will be equal to C1 times V all over C2 times V. But V1 and V2 are equal. This is just V. Then we can cancel that out. And therefore, it's proportional. Q1 over Q2 is proportional to C1 over C2. Then we can substitute the values for Q1. Q1 is 50 microfarad or just 50 because I will be dividing it with another micro. It's 100. So it will cancel out. So this will be equal to, or this is the capacitance. And this will be equal to Q1 over Q2. And Q1 is equal to, this Q1 here, it's not actually the charge across or the charge in the first capacitor, but this is the initial charge. So meaning this is the total overall charge that is being inside the two capacitors, because the other charge here from 300 microcoulomb will go to the another capacitance, the 100 microfarad capacitor. So this means that 300 microcoulomb here is the total charge. This is the total charge. So if we add Q1 and Q2, so the total charge Q total should be equal to Q1 plus Q2. What is Q1? This is the new charge in the 50 microfarad capacitor. And Q2 is also the new charge of the initially uncharged capacitor. So at t equals 0, the charge in C1 is 300. But when another capacitor is connected across, then the other charges from that capacitor, 50 microfarad, will be transferred into C2. So this means that the charge now of C1 will not be equal to 300 microcoulomb, but it should be lesser than 300 microcoulomb. Why? Because the other charges will be transferred to Q2 here. And this is equal to 300 microcoulomb. Then we can have two equations here. Q1, Q2, this is one equation and this is another equation. And we have two unknowns, Q1 and Q2. So from the second equation, or from the first equation, we can determine the value for Q1. So Q1 will be equal to 50 over 100, and that's 1 over 2 times Q2. And you can equate this to the second equation. So this will be 1/2 Q2, that's the Q1, plus Q2, and this should be equal to 300 micro. Then we add that 1/2 plus 1 is this equal to 1 and or 3 halves. So this will be 3 halves Q2 equals 300 micro. Then solving for Q2, this will be equal to twice 300 and divided with 3. And that will be equal to 200. This will be equal to 200 micro. The unit is coulomb. So the charge now that is transferred to the second capacitor is actually equal to 200 microcoulomb. And the charge at Q1 will be just half, or the half of this one will remain to, or 1/2 Q1 is equal to 1/2 of Q2. So 1/2 of 200 is 100 micro. So if we add them, it's also equal to 300 micro because that's the total charge. So 200 is transferred to the second capacitor and 100 is the remaining charge at the first capacitor. So if the question asks that the problem asks the remaining charge at the first capacitor, then your answer here should be equal to 100 microcoulomb. Okay? Another example, this one. A capacitor is charged with an energy of 0.23 watts second at a voltage of 48 volts. Now the question is, what is its capacitance? So this is a direct solution using the formula. Remember, 1 watt second is actually equivalent to 1 joule. So we can use our formula before here. The energy stored in a capacitor, that's just equal to 1/2 C times the voltage squared. So we are solving for the capacitance. We are given with an energy which is 0.23, so that's W. And we are also given with a voltage 48 volts. So the formula will be W equals 1/2 C times the voltage squared. Then the energy is 0.23. This is now in joules. Joule, or we don't need to convert this one in joule because it's now in joule. But if the problem gives you another unit, then you need to convert it first in joule before you use the formula. So 0.23 watt second, and this will be equal to 1/2 times, we're solving for the capacitance, and the voltage across it is just equal to 48 volts. And you square that, and that will be our capacitance. So 2 times 0.23 divided by, so the capacitance will be 0.23 times 2 divided by 48 squared. So C, the capacitance of the capacitor will be equal to 200 microfarad. Another example here, the net capacitance of C1, which is equal to 6 microfarad, and C2, that are connected in series, is 3 microfarad. Now, determine the capacitance C2 in microfarad. So, we take note, this is in series. So, if we are in series, what's the formula for the net capacitance or total capacitance? So, the total capacitance will be equal to, we can use the formula C1 times C2 all over C1 plus C2. This is the formula for the parallel version of two resistors, but they are in series and this is capacitors. Then we use the formula in parallel for resistors. So C1 times C2 all over C1 plus C2. Then we want to determine the value of the second capacitor C2 given the net capacitance, which is equal to 3 microfarad. So this is 3 micro, or we just use 3 so that the output of this one will be in terms of micro. So 3 equals C1. C1 is what? C1 is 6 times C2 all over 6 plus C2. Then solving C2 here, so we can cross multiply. So this will be 18, 6 times 3 plus 3C2 equals 6C2. Then this will be, we'll put this one on the other side, so 6 minus 3, then 6 minus 3 is 3. C2 equals 18. Therefore, C2 will be equal to 18 divided by 3, and that is 6. And the unit here will be in terms of micro. So, the capacitance of the second capacitor, if the net capacitance is 3 microfarad, is then 6 microfarad. So, if you look at this 6 and 6, then because they're connected in series, so the capacitance will go down, and it actually half of the two capacitors or capacitance, which is 3 microfarad. Another term they use for capacitors, if you encounter this term, they call it the condenser. So that's the another term for capacitor, condenser, before they call it condenser. This is another example. a condenser of 1 microfarad capacitance, so condenser means this is a capacitor, is charged to 100 volt and then disconnected from the power supply. A second but uncharged capacitor of 3 microfarad is then connected across the first capacitor. Now determine the voltage across the parallel combination. So this is somewhat similar with our example here, this part here. But instead of giving the charge inside the capacitor, it gives the voltage across the capacitor before it is disconnected. And we can solve for the capacitance using that voltage or the charge using the voltage formula. Then we can apply what we did from that example. So how do we do that? So we know that Q or the charge, this is let's call it Q1, the first charge will be equal to the capacitance of the first multiplied by the voltage. So this is the first voltage of the capacitor 1, which is this is the initial voltage now. So C1 is 1 microfarad. So 1 micro. You multiply it with 100 volts. So the initial charge now will be equal to 100 microcoulomb. So this is the initial charge. This is in the capacitor 1. Then, what will be the total capacitance? Because they are connected in parallel, what happens to the total capacitance? So the total capacitance will be just equal to the sum of the two, C1 plus C2. C1 is equal to 1 micro plus C2 is equal to 3 micro. So this is just equal to 4 microfarad. Then we can use this to solve for the voltage across the capacitor, the parallel combination. Remember, Q1 here is 100 micro. So what's this 100? This is actually also the total charge, just like what we did with the previous example. This is the total charge now. So if we solve for the voltage now, using the formula Q total, Q will be equal to the voltage times the capacitance, the total capacitance multiplied by the voltage of the parallel combination. So we already know QT or total Q, that's 100 micro, and this should be equal to the total capacitance, 4 micro, then you multiply it with the total voltage. So what will be the voltage? This will be equal to 100 micro divided by 4 microfarad, or 4 micro, and this will be equal to 25 volts. So the voltage now of the parallel combination is 25 volts. Last example for capacitors. 3 capacitors A, B, and C are charged as follows. For the first capacitor, capacitor A, which has 10 microfarad capacitance, is being charged by a 100 volt source. For capacitor B, it has 15 microfarad capacitance and being charged at 150 volts. And for capacitor C, 25 microfarad capacitance and being charged with a 200 volt source. Now, they are connected in parallel with terminals of like polarity together. What is the voltage across the combination? So this is the initial condition. They are being charged with different sources. Then after that, they are disconnected and connected with each other in parallel. Now the question is, what is the voltage now of the combination, the parallel combination? So first, we need to determine the total charge of the 3 capacitors. Okay? So what will be the total charge of the capacitor? We just add them. So the total charge will be equal to the charge at capacitor A plus the charge at capacitor B plus the charge at capacitor C. And what's the formula for the charge? Charge is just equal to the product of the capacitance and the voltage. So for A, This is equal to C, capacitance of A is 10 micro. You multiply this one with the voltage, 100 volts for the capacitor A. For the capacitor B, this is 15 micro multiplied by 150 volts. Then for C, it's 25 microfarad multiplied by 200 volts. And this will be our total charge of the combination. So this is equal to 8,250 microcoulomb. Then, because they are connected in parallel, what will happen to the total capacitance? So, total capacitance will be the sum of the individual capacitors because they are connected in parallel. C1 or CA plus A plus B plus C. A is 10 micro, B is 15 micro, plus C is 25 micro. So the total capacitance now will be equal to 10 plus 15 plus 25, that is 50 microfarad. Then we can now determine the voltage by using these two. The total voltage using the formula, or Q is equal to E times charge. So Q total is simply equal to the total capacitance multiplied by the total voltage. So total voltage is the voltage across all the capacitors because they are all connected in parallel. Then the voltage across them are all equal to E total. So QT is equal to 8,250 micro. C total is 50. Then solve for the total voltage. So total voltage will be 8,250 micro divided by 50, and that is equal to a 165 volts. So the voltage across the combination of the three capacitors now will be equal to 165 volts. So this is all about capacitors. So the next topic will be about magnetic circuits.